So today, the aim of the lecture today is to prove the Kobayashi-Oshai theorem for foliation. So let me remind you. So this is theorem. So actually, this theorem was proved a long time ago with Stefan and Sander Kovac. So in 2008. But the proof that I'm going to give today is it's a different proof, and it involves tools that can be used to prove further results. So let me remind you the statement. So X is a smooth projective variety. And F is a funnel foliation on X, and then it will have a certain index with index I of F. And then what we prove is a bound for the index in terms of the rank. Let's say index I and rank R. Then the index is bounded by the rank. It's less or equal than the rank. And the equality holds if and only if X is isomorphic to Pn and F is induced by a linear map, a linear projection. Okay, so as I said, the proof that I'm going to give is different than the original one, and the tools that we're going to use can be used to prove stronger results. So for instance, let me just say that remember that in the Kobayashi-Oshai theorem, we had a bound for the index of a funnel manifold, and as I mentioned, we had then a classification of the next cases. So we can do the same for foliation, so we can define so a funnel foliation with next possible index, with index equal to the rank minus 1 is called the del peso foliation. And we have actually investigated these foliations also, and we have some partial classifications under some restrictions on the singularities. And notice that here, in particular, in the case of highest possible index, the leaves are algebraic. They're just linear subspaces of Pn. Now, in this case here, in the del peso case, leaves need not be necessarily algebraic. So for instance, we can start with Pn, take a linear projection to some Pm, and here we can take a foliation that is given by a global vector field. So if I take this vector field general, this foliation is going to be transcendental. So this is OPM. And then on Pn, I can take the pullback, so let's call this linear map phi, the foliation defined as the linear pullback of this foliation G. So if you compute so if I put this, let's say, n minus r plus 1, so this is the m. If you compute the anticanonical class of this foliation, you will see that O minus Kf is O of R minus 1. So this is an example of del peso foliation. And we see that if we choose the vector field general, this is going to be transcendental. And so the leaves here are not algebraic. And so one of the things that we proved is that this is the only case. So if you have a Del Peso foliation on some projective manifold which is not Pn, then the leaves are necessarily algebraic. And let me just remind you a theorem that I stated in the first lecture. So in fact, we have something else, like under this condition, so xf, a funnel foliation on a smooth projective variety x. Then we can have a bound for the algebraic rank of the foliation in terms of the rank, of the index. So this is the algebraic rank is greater or equal than the index. And moreover, equality holds if and only if, again, x, we are in a case like this one here. So we have that x is isomorphic to Pn. There is a rational map to some Pm. And here I have some foliation G with trivial canonical class. And our F is the pullback, the linear pullback of this foliation. So this is a general result. And in particular, for Del Peso foliations, if we are not in Pn, then the leaves are algebraic. OK, so and in fact, we can say more. We can replace the condition of being funnel, but by just asking that the anticanonical class is big, and measure the positivity by that modified index that generalized index that I introduced in the first lecture. So the tools that I'm going to use to prove this theorem are actually the tools that we use to prove this stronger version, and actually even classification of the log leaves of Del Peso foliation. So as I go through the proof, I will point out points where it can be used to prove stronger results like this. OK, so let me now remind you of the main tools, the main theorems that we are going to use. So the first one is the theorem of Bost, Campana-Pound, that I stated in the first lecture. So again, let's take F, a foliation on X. So for this lecture, X is always going to be a smooth projective variety. And let me take alpha, a class of moving curves on X, on 0. And then we have a notion of stability with respect to alpha. And the condition here is that, so we suppose that the foliation is alpha semi-stable with positive slope. And the conclusion is that F is algebraically integrable. Then the leaves of F are algebraic. And as I mentioned, they prove more. They prove that the leaves are rationally connected. But for us, this is going to come for free from our assumptions. So now I have to make a decision. It's my last class, and I promised you that I would return to the proof of the theorem that was a bit rushed in the first lecture. And so I think I will actually do that. So let me again, now with a little bit more time, give you the idea of the proof. And so the first step is to consider the analytic graph of the foliation. So we consider the analytic graph of the foliation. And so Stefan reminded us what it is. So what it, let me just make an assumption. So for simplicity, we will assume that the foliation is regular, so that there's no, the singularity is empty. So that means that F is in fact a vector bundle, and it's a subbundle of the tangent bundle of X. So in general, the complement, the singular locus of F has codimension at least 2. So we have to work on the complement, but since it is a big open subset, the proof can be made to work in this case. Okay, so we consider the analytic graph. So what we do is we embed X in the product by the diagonal, and here we consider the analytic graph, which is, locally, again, at every point, F is just a product, and here we look inside the diagonal of X. We take this picture here. Take little pieces of the fibers. So when you restrict to a fiber of the second projection, what you're getting is a piece of the leaf through the point X. Okay, so let me call this analytic graph V, and what we want to show is that, so what we want to show is that the V is algebraic. And in other words, we want to, when we take the Zariski closure of V, let me call this V, we want to show that this has dimension exactly equal to n plus r. N is the dimension of, let's say, of X, and R is the rank of the foliation. So we want to show that this has dimension n plus r. And now let's look, let's formalize this. Let's consider the formal neighborhoods. So let's say, so now we formalize. So let me now call V hat the formal completion of V along X. And now this can be, now this is where the foliation appears. So here, the normal bundle of X inside V is precisely the foliation F. So this is the important property that we want. And so in other words, we can describe the conormal, so the ideal sheaf. So the ideal sheaf of X inside V modulo Ix square is nothing but the dual of the foliation. And when we look now at successful infinitesimal neighborhoods of X inside V prime, what we get is the following. So as usual, so we have maybe X naught is X contained in X1, contained in x2, and so on. And here the ideal sheaf of the xi is just the ideal sheaf of x to the power I plus 1 inside OV. And now if I consider the completion, then what I get is that, so now what we want to show that this has dimension n plus r. So we want to show that, that for some ample line bundle A, say on x cross x, I want to look at global sections in V hat of A to the power D. Well, now maybe I will just, okay, so this is restricted to V hat. We want to show, in order to show that the dimension is n plus r, we have to show that this grows at most as O d n plus r. So this is what we need to show. Okay, but now what we do is to look at the restriction of A to the successful infinitesimal neighborhoods. And what we have then is the following. So we have that, we will have, let me call, so the inclusions, so these inclusions will induce restriction morphisms on the space of sections. So now restricted to x naught. X1, and so on, so x naught. But we can say exactly what is the kernel of this map. So the kernel, so this follows from this description here of the ideal sheaf of x. So this gives that the kernel of Qi is nothing but, so this is going to be the global sections on x, A to the D, restricted to x naught. So here on x naught. Now tensored. So now comes this part here. We will get the sim I of f I of f dual. So now this is these are the kernels, and now what we want to prove is then and this is just this this inverse limit. So what we want to prove then, so the dimension of this space of sections is just the sum of all these kernels. So the dimension and so this is what we want to show that grows at most like this. So the first thing that we show is that eventually this becomes 0. And this now, so the first, so now we notice that, so A, the observation, the first observation is that if you take dx naught that this becomes 0 whenever I over d is greater than some delta naught fixed constant. And this comes from the stability condition. So let's see what this is. So observation, so we know, we're assuming that F is alpha semi-stable with slope, let's say, with positive slope with respect to alpha. So this implies that any symmetric power of F is also alpha semi-stable with slope I times I naught. And this is 0. Now, if we have a section here, so a section here will correspond to a map from sim IF to AD. Now, because this is semi-stable and has this slope, I can look at the kernel, and the kernel of this map have to have smaller slope. So that means that this one has to have bigger slope. So the slope of, so if I look at this slope, we get an inequality. So the slope of this one, which is, say, I mu naught, must be smaller than the slope of this one, which is d times a dot alpha. So I see that then I have to have I over d must be less or equal than a dot alpha divided by mu naught. So this is what I take to be this constant here. So we see that eventually, well, eventually with this condition here. Now this depends on the I and the d. Vary this way, I get that everything is 0. So this is the first observation, and then let's see what we get. Maybe I want to keep that theorem. And so what we have so far is that we have that the dimension of that space of global sections is equal to the sum now for I less or equal than delta naught d of this of the dimension of those kernels. Okay, but now we notice the following. So this space of global sections, and here I am assuming that F is a vector bundle. So this is nothing but, if I look at the projectivization of F dual mapping to X. So this has rank R, so this is a P R minus 1 bundle. And this is nothing but the space of global sections on this projectivized space of, here I have to pull back A, and this becomes just, I'm tensoring with O, P, I. And now this grows, so this dimension here, as D grows, this grows at most as D to the N plus R minus 1, because this is the dimension of this space here. And now if you put this together, we have N plus R minus 1, but we also have the D here. So this, putting together, this grows at most as O to the D N plus R. And this is exactly what we wanted. OK, so this was supposed to be done in the first lecture, but that's OK. And now we are going to move to something completely different, which is I'm going to give you the proof of that theorem. OK. So proof of Kobayashi-Oshai for foliations. OK, so the first step. So what we are going to do is the following. Let's first assume that we know that this foliation F is algebraically integrable. And once we know that it is algebraically integrable, we are going to use properties of the log leaf we are going to use MMP to actually describe precisely what the log leaf has to be, and then use it to recover Pn. OK, so so let me see. Let me fix some notation here. So let's suppose that the index is at least R. We are going to prove that the index is exactly R and that we are in Pn. And so what does that mean? So that means that our minus, let's say, minus Kf is some R plus epsilon. Epsilon is a positive or non-negative integer times L. Well, L is ample. OK, so let's assume, so part 1. So let's assume that the leaves are algebraic. And let's call a general leaf a general log leaf F delta. I used the prime yesterday when I defined it, but I'll just drop it so that the notation gets simpler. So we let F delta be a general log leaf. So remember, that means that F is the normalization of the closure of a general leaf. And we have the adjunction formula that the canonical of F plus delta is the pullback of the canonical of the foliation, which in this case is R plus epsilon L. So let me, okay. So this is what I'm going to do. Let's take, so this is what we are going to do. We are going to take, so we have F here. Let's take some, we don't know, in principle, F is just normal. It may be very singular. So let's take F tilde, the singularization. And let me pull back this ample divisor L. So this is no longer ample, but this is nif and big. So this is the pullback of L. And now the idea is the following. We are going to run a certain MMP on F tilde. And this is going to, and we're going to see what happens in the end. So let me use the next blackboard. So this idea of running the MMP, a suitable MMP for the log leaf, is due to Andreas Horing, and it can be used in many contexts to give us a very concrete description of the possible log leaves. So we notice the following. So there, we have F. Here we have the desingularization F tilde. Here, let me call this L tilde. And notice the following. So we have, one important thing is, so we have that Kf plus delta is minus R plus E times L. And so we see that Kf plus R times L. So this is minus epsilon L minus delta. Now I claim, and this follows from a theorem that I stated yesterday, I claim that this delta here is non-zero. So let me remind you, maybe I'll leave it on this part of the blackboard. The special property of algebraically integrable foliations, with which I ended last lecture. So reminder, we ended with the follow proposition. So X, smooth projective variety, F, algebraically integrable funnel foliation, we saw that if the general log leaf is log canonical, then there is a common point. There is a point on delta whose image is in the closure of a general leaf, whose image in X is in the closure of a general leaf. So in particular, this says that whenever I have a funnel foliation, so in particular, consequence, if I have F, an algebraically integrable funnel foliation with log leaf f delta, then the delta is non-zero. And this is because, remember, the points of delta are exactly the points, correspond to the points through which I have an infinite dimensional family of leaves. And so if the delta is 0, that means that I actually have locally a fibration. But if I have locally a fibration in particular, the delta is empty and the F is smooth. And this is log canonical. And so this cannot happen. I must have a common point. And so this shows that in this case here, the delta is non-zero. And so in particular, this divisor here is not psif. It is linearly equivalent to something, to minus something effective. So this is not psif. This is not psif. And then when I look in F tilde, this will give me that F tilde plus R L tilde, again, is not psif. And so what I will do is I will run KF tilde plus R L tilde MMP. And this is OK because this was, I can take this to be KLT. And then because this is not psif, actually, I do have an MMP that ends. And now let's see what happens at each step of this MMP. OK, let's look at the first step. And let me remind you how the MMP works. So let me call this F1. So what is this? So we pick, remember that we pick KF minus RL negative extremal ray. So this is the first step of MMP. So in the first step, we pick an extremal ray such that K F tilde plus R L tilde dot C is negative. And let's see what happens if, let's investigate this intersection number with L tilde. So if this is non-zero, then, well, this has to be positive. This is nif and big. And so that means that the KF tilde dot C has to be minus KF tilde dot C is going to be greater or equal than R dot L tilde dot, greater than this dot C. But this is at least 1. So this is at least R plus 1. But now this is a smooth projective variety of dimension R. And we are picking an extremal ray. And remember that this extremal ray, we always had that this was between so we had that. So this is an extremal ray, a k-negative extremal ray of dimension of length r plus 1. So remember that in this case, this implies that actually f tilde is PR. So this was the theorem on the bound of the length of extremal rays that I mentioned when I introduced MMP. And in this case, this would be PR, which is the singularization of a normal variety. So in particular, this would tell us that the F itself is PR. So the leaf is PR. And because of the adjunction formula, well, we would need that the delta has to be the epsilon is 0, and the delta is a linear PR minus 1. So this would give us the log leaf in this case. So this is if the intersection of L tilde with C is non-zero. But if the intersection of L tilde with C is 0, when we look at the contraction of this extremal ray, so this contraction goes to some Z here, and then we have a diagram like this. So either this is a flip, or this is just the identity, and this is a divisorial contraction. But in any case, what we are seeing is that if this L tilde dot C is 0, this means that it has to factor, the map from F tilde to F has to factor through Z. And so what we get here, again, is a map to F. And here we have the L1, which is the push forward of L tilde, is in fact a pullback of the original L from F. So here, then we get the L1 is the pullback of L. And then we can continue. And so eventually, this is going to end. And it will have to end in this situation here. So there is a slight subtlety here, which is when after I run MMP, so for instance, this could be a divisorial contraction, and this could no longer be smooth. This would be terminal, Q factorial and terminal, but still, there is a theorem by Andreatta that guarantees that still in this context, this long extremal ray can only occur in this situation. So there is something that is so there is some theorem behind, but this can be made to work. And so the conclusion is that in the end, so the conclusion again is that when we finish MMP here, it has a map to F, and it has to be Pn. So the conclusion is that, in fact, F is isomorphic to Pn. The L, the pullback of L, is O1. And the delta is a linear Pn minus 1. Okay, so let's see what this means. So I have the F delta. So this is our F delta. It's a Pn with a hyperplane section. Now this is in particular log canonical. Sorry, PR, yes, you're right. Thank you. And this is PR minus 1. Now, this is in particular log canonical. And then, again, we can apply this proposition implies that there exists a common point. Let me just make a quick remark here. In fact, for those who know more about MMP, let me say that this proposition here is stronger than, the result can be made stronger than I stated. Not only there is a common point in the closure of a general leaf, but in fact, there is a whole log canonical center which is in the closure of a general leaf. So in fact, in this case here, the stronger version of the proposition would tell us that this whole PR minus 1 is contained in the closure of every leaf. So we don't need this, but it may be useful in other situations. But see, let's see what this tells us now about X itself. So here we are in PR, and in PR we have lines. So let me denote by this common point by X on the fiber. And we know that on PR, we can connect any point to X by a line. So a line here, I mean just a line here, it has intersection 1 with the L. So when I look at on X, so on X, this common point X can be connected to any point of X. Y by a line. By a line, I mean an image of one of these lines. And now this is something very strong. So this almost immediately shows that X has to be Pn. And this is because the fact that X can be connected to any point by a line implies that the Picard number has to be 1. And so, and the index, so it is in particular a Fano manifold, and the index can also be computed by, can be derived from this description, because if I look at, say, Vx, the family, or even Vx, the family of lines through X, then this dimension here, this is a general fact in the deformation theory of rational curves. This dimension here is precisely the anticanonical degree of L minus 2. And now, since X can be connected to any point, this dimension here has to be at least n minus 1. And so minus kx dot L has to be at least n plus 1. But this is nothing but the index of the Fano manifold, because this is this index of X times the generator L dot L. And so this tells us that the index is n plus 1. And then by Kobayashi-Oshai, we conclude that X has to be Pn. So index equals to n plus 1. Then by Kobayashi-Oshai, we know that X has to be isomorphic to Pn. And we have a description of the leaves. And then from there, it's easy to conclude that actually F comes from a linear projection. OK, let me point out that this argument here still works if I am in the case of del Pezzo foliations. So this argument allows us to give a complete classification of all the possible log leaves of a del Pezzo foliation. OK, so now it remains to show that the leaves are algebraic. OK, so now it remains to show, so this is part 2 of the proof. To show that the leaves are algebraic. OK, so now we want to apply, so I erased, but we want to apply Campana-Pound. So let's fix some, I suppose, so let alpha be a moving class. So if F is the non-zero moving class, so if F is mu alpha semi-stable, then we are done. Then leaves are algebraic. And so if not, now we can consider a maximal destabilizing subsheaf, and this one will have algebraic leaves, and then we are going to see that these leaves would have to carry, this subfoliation would have to carry too much positivity. So we take F1 inside F, the maximal destabilizing subsheaf. And so we know that the slope of F1 is bigger than the slope of F. But we want to use a little bit more because we know we are assuming that, remember that K minus KF is R plus epsilon L. And so, in fact, we can, using this, we actually can bound this slope. So what we get is that this slope of, let me call this, so this has rank R, and this will have rank, say, R1. So in fact, what we have is that the slope of F1 twisted by RL minus R1 is greater than the slope of F twisted by L minus R. So I'm just adding R's, but we know that this, by assumption, this is greater or equal than 0. So this is this assumption here. And so we actually know that the slope of F1 tensor by minus R1 is in fact positive. But so this is telling us that minus KF1 minus R1L dot alpha is positive. So in particular, kf1 plus r1l is not psif. And so now let's look at the leaf of f1. So let's let f1, do I want to delta? Maybe I don't need the delta now. So let f1 be the leaf, the closure of a general leaf of f. And now there is a claim here that, so in general, you start with some divisor which is not psif. If you restrict it to a subvariety of x, then there is no reason why this property is going to be preserved. But if I take f to be the leaf of an algebraically integrable foliation, then this is true. So this, actually, one can prove that this implies that when you restrict to the closure of a general leaf, then you have that kf1 plus r1 L restricted to f1, or even the normalization. Then this is still not psif. And then one can run exactly the same argument that we did here. So see, all that we needed is that kf plus RL is not psif. So we can run the same argument as in step 1 to conclude that the leaves here are projective spaces. So, same argument as in step 1 shows that F1 is isomorphic to PR1. Okay, so actually the reason why I did this, I just wanted to conclude that our variety X has many rational curves. So in particular, to have many lines coming from this leaf. So this would follow if I already used the fact that the leaves of F1 are rationally connected, but since I did not prove that, I just got the rational curves in a different way. Okay, so now this is what we are going to do. So here in particular, we have many lines. So let's say I'm going to call L the image of these lines in X. And they have degree 1 with respect to L. So let me call V the family of lines on X. By lines, I mean family of curves in the same component, say in Shao, of the image of those lines. Okay, so maybe I want to make a remark here, which is, so before I do this, let me just make a remark. If the Picard number of X is 1, then any stability here, any slope stability is equivalent just to, they are all equivalent, and this is just equivalent to taking, instead of taking this to define the slope as the index divided by the rank. So if the Picard number of X is 1, then this condition here would imply that the index, that the F1 is a Fano foliation, that F1 is a Fano foliation with index greater than the rank. And then this is impossible by the first step, because now we know that F1 is algebraically integrable. So which contradicts step 1. So we can assume that the Picard number is greater than 1. And we are going to consider the rationally connected quotient with respect to this family. So let me tell you what this is. So let me just do a digression here, and then the rationally connected quotient. Sorry? It is here. Yeah. Because this slope can be defined to be the index divided by the rank. They're all equivalent to this. All slope conditions are equivalent to this. Okay, so I'm taking here this family of lines, and so let me call the rationally connected quotient with respect to V. So this family here, this is a proper, because of this condition here, this is a proper family. Meaning that you cannot, the family of curves, so if I take a family of curves here, it cannot break into something else. So this is a proper subvariety of Schau. And so the rationally connected quotient is as follows. So I can take, inside of X, I can consider the following equivalence relation. I say that 2 points, X and Y, are equivalent if they can be connected by a chain of curves in V, lines in V. So, and now I want to realize this equivalence relation algebraically, meaning is there a morphism from X to something else whose fibers are precisely the equivalence classes? And the answer is that yes, up to shrinking X a little bit. So there is a dense open subset X naught in X and a proper morphism from X naught to, say, Y naught with the property that the fibers of, let's say, pi are equivalence classes of the V rationally connected equivalence relation. So what I have is that the fibers, 2 points on a fiber can be connected by a chain of lines, and 2 points in different fibers cannot be connected by a chain of lines. Okay, so now I have this map, and I want to investigate how the foliation behaves with respect to this fibration. So if the F restricted to the X naught is contained in this relative tangent, then I can restrict, so that means that it will induce a foliation with the same properties. Or here, maybe I'm looking at F1. No, I want to look at F. So if F gives me, fact is contained in the relative tangent, that means that I can have on the fibers of pi, I have this foliations F, which have the same property as the statement, and then I can apply induction on the dimension. So if this is true, we can restrict to a fiber, general fiber of pi, and apply induction on the dimension of X. And so we may assume that the F is not contained in the relative tangent. Well, if it is a point, then the Picard number is 1. So let me just put this remark here. Remark. So if y is a point, then the Picard number is 1, exactly because I'm saying that any 2 points can be connected by a chain of lines, and then we are done by this observation here. Sorry?
Like product of two projective spaces?
Yeah, but I'm fixing one family of lines. So in this case, I would be fixing a family of lines in only one factor. Okay, so sorry, I am a bit confused with these blackbirds. Okay, so let me just recap. We are fixing a family of let's call them lines. So these are rational curves which have degree 1 with respect to this ample line bundle L. And we consider the rationally connected quotient. And we can assume that our foliation F is not contained in the relative tangent. So now, if I take L, so let L be a general line in this family. And here, we need to know a little bit of the formation theory of rational curves. But let me tell you that under this situation, the restriction of the tangent bundle to L has a very special form. It can be decomposed in this way for some value of D, which will depend on the intersection with the anticanonical. So this O2 here is just the inclusion of TL in this restriction. So this is this O2. And this O1 here, so this gives you the directions under which you can deform the curve with one point fixed. And notice that this part here, so this is given by the, if you fix a line, then this O2 is given by this tangent direction. And this part here at a point is given as follows. So you fix another point, and then you deform the curve with this point fixed. And so this is going to sweep out some subvariety. And the tangent space at this point is exactly this positive part here. So, so this is just to tell you that this positive part is actually contained in the relative tangent of x naught with respect to y naught. This positive part is necessarily contained in here. And now let's look at our foliation f. So let's look at the foliation f and see how it restricts to L. So this has rank R. Degree equals to minus kf dot L, which is R plus epsilon, for some epsilon. And it must be contained, and so it's contained in TXL. And we are assuming that it is not contained in the relative tangent. So there is not many possibilities. It has to have the degree at least as big as the rank, and it cannot be all positive. Otherwise, it would be contained in the relative tangent. So there is only one possibility, which is that this restriction is of this form. So epsilon is 0, and we have this R minus 2 plus O. So this is the only possibility for this restriction. But notice the following. Notice that this O2, as I said, this is the tangent bundle of L, of the line. And so what this is saying is that this O2 here is telling me that the lines on the family are tangent to the foliation. So this is telling me that lines are tangent, lines on this family, lines of family V, or the general line of the family, are tangent to the foliation. But the rational connected quotient exactly tells me that this tells me that in particular that all the fibers of the rationally connected quotient are contained in leaves. And so what we get is that, in fact, the relative tangent is sort of contained in F. Well, maybe I have to shrink X a little bit, but what I have, or shrink Y a little bit, and then I have this. But then in this case, see again, it's not difficult. If you look at this restriction, it's not, so there is only one factor here left, and it's not difficult to show that in this case, X naught to Y naught is a P, let's see, R minus 1 bundle. And my foliation, and there exists a foliation G on Y naught such that F is the pullback of G. This Y naught may not be in general, it's not proper. But in this situation, when we are considering the rationally connected quotient with respect to lines, then one can show that this can be extended in codimension 1 on x naught. So remark. So because these are lines, can assume that the codimension of x minus x naught is at least true. So these are big open subset in X, and in particular, they contain many complete curves. So let me say, so complete curves. Just by taking, say, general complete intersection of very ample divisors. So I have these complete curves, and now let's say what this means. So I have the relative tangent. So let me restrict to well, in general, I have this. So this was what I was writing here. And here I have pullback of I'll have something, some g coming from the base. And if I restrict this to, if I look at the complete curve on C naught, maybe take the normalization and take the fiber product, I can assume, I get the following. So what we know is that this has ample determinant. This one cannot be ample. So this has ample determinant. This one, the determinant cannot be ample. Remember, when I have a funnel foliation that is algebraically integrable, I must have a common point in the leaves, and this is not the case here. So when I have it cannot be a fibration. So when I look again over, let me do this. This is going to be a bit quick, but if I restrict this to xc, so this is, okay, let me write it this way. So when I look at this in C, so again, this has ample determinant. This determinant cannot be ample. And so this is coming, so now if well, maybe I take something smaller, a bit smaller here, but in any case. If I look, this has ample determinant. This determinant cannot be ample, and so this forces this G, which is now something pulled back from C. This must have. So G dot C must be positive. So I'm just taking a curve. I'm taking a curve C. I look at the image of C. So this is a complete curve in X naught. And then I look at the inverse image. So this is a P R minus 1 bundle over this curve C. Maybe I have to take a normalization, but it's, the idea is that I just look at the inverse image of a complete curve. And see, what we are seeing here is that the intersection of G with C, now this is just a line bundle, this has to be positive. Otherwise, this would be ample. Right? If this is ample and this has negative degree, this will be ample as well. And so, but this is now we can apply, again, Campana-Pound. To conclude that the foliation that we get on Y, the G, has algebraic leaves. And then the foliation F itself has algebraic leaves. So this was sort of a sketch of the proof, but at least I think I showed you the main ideas involved and with which we can actually prove those stronger results that I stated. So I think this is all I wanted to tell you. Thank you.